Thank you very much. So as Peter said, my name's Adam Bouland. I'm a postdoc at UC Berkeley and also a technical advisor for QC Ware. And I study quantum complexity theory, which is the relative strengths and weaknesses of quantum computers. And today I'll be talking about quantum algorithms and kind of the landscape of their possible implementations on near-term devices. So Peter just finished giving us a nice talk on quantum hardware, which is about how will we build quantum computers. And the reason that people are excited about this is that we're now entering what John Preskill has called the noisy intermediate scale quantum era, or miscue era. That is to say, we'll soon have access to somewhat large, noisy and imperfect, but fairly large quantum computing devices, ones which are better than we've ever had access to before. And the reason that these are exciting is that these are the first quantum computing devices that we've constructed which might have beyond classical computational power. So in this talk, I'm going to be talking about quantum software instead of hardware. So I'm going to be trying to address what types of problems can we use quantum computers to solve, and what algorithms will we be using to solve them on the quantum hardware. And the reason that this is a very important field of study is that quantum computers do not speed up computation in general. It's not like building a computer that's 10 million times faster than your laptop. Rather, they're actually only faster than classical computers at certain specific applications, certain specific computational tasks. So it's very important to understand what quantum algorithms we have, because it tells us what tasks we'll be able to find quantum speedup for. And furthermore, these different quantum speedups have different degrees of the amount of speedup, or our theoretical evidence for that speedup, and also different degrees of feasibility on near-term hardware. Some algorithms look like they'll be easier to implement than others in the next few years. So the goal of this talk is going to be to try to give you a very high-level survey of the quantum algorithms that we have to date, and explain what sorts of speedups they have over classical computation, and how much evidence we have for these speedups, and also try to give you an idea of their feasibility on near-term hardware. And in order to achieve this goal, we're going to use two technical tools. So what controls the degree of speedup of these algorithms is something called computational complexity theory. And this is the study of the difficulty of computational problems. In particular, quantum complexity theory focuses on the relative strengths and weaknesses of quantum devices. So this is the lens through which we'll be interpreting our evidence for the computational power of these algorithms. And to address the second issue of feasibility on near-term hardware, the key variable that controls this is the degree of noise tolerance of the quantum algorithms. So some quantum algorithms that exist seem to be very robust to noise, and others not so much. And the near-term devices, the near future, will have a substantial amount of noise. In particular, they will not be performing something called quantum error correction. So quantum error correction is a way of redundantly encoding quantum information in many physical qubits in order to protect it from errors. And this is something that we believe we'll be able to achieve in the long term as we scale these devices, but this error correction comes with very high overhead, so it's a bit out of reach of these near-term devices. So the degree of the noise tolerance, therefore, is what's going to control how feasible they are on near-term devices. So to put this in more business language, what we're trying to ask is, what problems will quantum computers be useful for? How big of an impact could they have on a business? And this corresponds to how much speedup they have over classical computing. And finally, when will this happen? When could this impact happen? And that's really controlled by its feasibility on near-term hardware. So in order to conceptualize the landscape of quantum algorithms, I'm going to be referring very frequently to this chart. I'm going to try to categorize known quantum algorithms into one of 6 classes based on a few of their properties. So the first property, which is the vertical axis, is the amount of quantum speedup that's present. So I'll put algorithms that have a large speedup, what theoretical computer scientists call an exponential speedup, in the top row, those with a small or polynomial speedup in the middle row, and those with an unknown speedup in the final row. So this final row will be algorithms for which we haven't been able to prove a speedup, and one may or may not exist. We'll have to kind of test it empirically to see what happens. And what this translates to is, this roughly translates to how much these algorithms could impact the businesses which care a lot about these particular applications. So the exponential speedups can have, a very large or transformative impact in that area. Small speedups may or may not matter depending on the specifics of your application. If you have a very big bottleneck in that area, a polynomial or a quadratic speedup could be a game changer. And if that's not the bottleneck, then it might be less useful. And for the unknown speedups, we don't really know yet how much this could impact the business. Now, the second axis I'll be categorizing the quantum algorithms on is their degree of feasibility and their degree of noise tolerance. And this roughly controls when these algorithms could have an impact in the enterprise. So you can see that kind of where we want to be on this diagram is the upper left-hand corner. We would really like to have quantum algorithms that have provable exponential speedups over classical computing and that are noise tolerant so they can be implemented in the near term. But what we'll see as we go through this talk is that most of the algorithms that we know of today fall in this part of the diagram. The algorithms for which we have more provable speedups or more theoretical evidence for speedups are often things that will require error correction, so are more long-term feasible. On the other hand, many of the near-term algorithms, we don't have a good idea yet of what their speedup will be. So it will end up being a matter of empirical implementation of these algorithms to see how they do. So this is why it's kind of a very exciting time in the history of quantum computing is we're finally going to be able to test out some of these near-term algorithms within the next few years. Great, so I'm going to try to run through these algorithms in order of their area of application. So I'll be going through them. So the 5 main applications of quantum computing that I'll be discussing are simulating quantum systems, optimization, machine learning, cryptography, and quantum supremacy. I'm going to try to go through these one by one to give you an idea of what's known in each of these areas and what are their near-term prospects. All right, so let's start with simulating quantum systems. So in some sense, simulating quantum systems was the original application of quantum computing. So when Feynman gave a lecture in the 80s, he had this really famous quote, which is, nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. So in this quote, this is, I believe, from one of his lectures in 1981 or 1982, Feynman was already envisioning a future in which we use quantum mechanical systems, engineered systems, in order to simulate nature, in order to simulate processes in quantum chemistry and in quantum physics. And Feynman, as in many topics of physics, was just ahead of his time. And in the intervening decades, this kind of intuitive observation of Feynman from the 80s has been made rigorous. So starting with works of Lloyd in the 90s and many subsequent works, computer scientists and physicists have shown that quantum computers can simulate quantum chemistry processes exponentially faster than we know how to do so with classical computers. And furthermore, we have very strong theoretical evidence that these exponential speedups are genuine. So for the experts in the room, this is because many of these quantum simulation and quantum chemistry problems are something called BQP complete. For non-experts, what this really means is that in some sense, quantum simulation is the most powerful thing that a quantum computer could possibly do. It kind of captures the full generality of anything one could do with a quantum computer. So as a result, this area of quantum simulation is believed to have many applications to many parts of industry, because there are many portions of industry in which simulating quantum systems play a critical role. So for instance, material science, chemical engineering, the design of catalysts, biomedical engineering, the processes of protein folding, theoretical physics. People are interested in studying the mechanics of black holes using these devices. There are many cases where a business important process is really dependent on quantum effects, and simulating these things with classical computers is prohibitively costly. So how feasible are these quantum simulation algorithms? Well, the quantum simulation algorithms, or quantum chemistry algorithms, in general fall into two categories, broadly speaking. The first category are quantum algorithms that simulate quantum dynamics. What do I mean by that? Is they study how quantum systems evolve over time. So the physicists call this Hamiltonian simulation, but it really just means how quantum dynamics change over time. And for these problems, we have very strong evidence for speedups. But these applications are not quite in reach of near-term devices. So there was a very nice paper in 2016 by the Ware et al. And many people from the Microsoft group, which gave explicit gate counts for simulating a particular catalyst called nitrogenase, which is used in the Haber process of fixing nitrogen for fertilizer. And while they did a great job of trying to optimize and explicitly count how many gates and qubits one would need to perform this algorithm, it seems to be a bit out of reach of these near-term devices. So these Hamiltonian simulation algorithms look like they're not in the short term, they're more in the medium or long term. Now, the second category of quantum chemistry algorithms are algorithms that are trying to study quantum statics. So these are algorithms that try to understand if you have a quantum system, in what state will it naturally settle to after you evolve it for a very long period of time. So this is more analogous to statics and physics, where you have a bridge and you want to know what will be its reaction to various forces on it in some sort of stable configuration. And one of the prominent examples of such an algorithm is something called the variational quantum eigensolver, or VQE. And there are many other algorithms in this family of what are called hybrid classical quantum optimizers. And these algorithms have, I'd say, an unknown speedup. We haven't been able to prove that they have a complexity theoretic advantage, but there's some hope and optimism that they might. And these seem to be more in reach of near-term devices. So in short, if we were to go back to our landscape of quantum algorithms, if you want to know where quantum chemistry sits on this landscape, we see that the Hamiltonian simulation problems of quantum dynamics fall in this upper right-hand box. So they're algorithms that have exponential speedups, but they seem like they're something that will only occur in the medium or long term. And these VQE algorithms and some of these hybrid classical quantum algorithms fall in this box. So we don't quite have a good mathematical handle on what their speedup will be, but it looks like we'll be able to try them out soon. In fact, I believe there'll be a talk either later today or tomorrow about this exact topic. All right, are there any questions about quantum chemistry simulations before I move on to the next section? Okay, great. So next I'm going to move on to the next application of quantum, and this is applications to optimization. So as you all know, optimization is a ubiquitous problem in industry. For instance, as been mentioned, let's say you have a particular network of cities or of delivery points, and you want to make a circuit of them in the shortest or most efficient amount of time possible. Or let's say you're a financial company, and you want to find the portfolio that has the minimum amount of risk for a given financial return. All of these problems, when you abstract them mathematically, have the form of an optimization problem. You want to minimize or maximize some objective function subject to a certain set of constraints. And these problems are often computational bottlenecks because they tend to be very computational difficult in their most general forms. So for the experts in the room, this is because almost all optimization problems are something called NP-hard. And for the non-experts in the room, all this really means is that we do not expect to have general purpose classical algorithms that perform really well on optimization problems. Optimization just actually intrinsically has some sort of computational difficulty, which is a roadblock to having very fast algorithms. So how can quantum computing help with these very difficult problems? Well, the answer goes back to the early days of quantum computing. Namely, in the 90s, Locke Grover gave an algorithm called Grover's algorithm, which showed that quantum computers can obtain a polynomial speedup for optimization problems, in particular a quadratic speedup. And this algorithm is extremely widely applicable. It's been generalized to a primitive called amplitude amplification for the experts in the room. And this amplitude amplification primitive comes up everywhere in quantum algorithms. It can be used for optimization, can be used for database search, it can be used to improve Monte Carlo methods in finance. This was a recent paper by Montanaro showing this. This is a very general purpose speedup, and almost any optimization problem that you give us, it will almost certainly be amenable to a Grover speedup. So what's the downside of Grover's algorithm? Why hasn't Grover's been mentioned much in the previous talks? Well, the downside to Grover's algorithm is that the speedup that it exhibits is not something that seems to be amenable to near-term devices. There are two reasons for this. One is that there's a result of Zalka from 1996, which shows that the Grover speedup intrinsically requires large depth quantum circuits. So this means in particular that the quantum computers that we have in the near term will only be able to perform very shallow depth circuits because of the fact they aren't performing error correction. And furthermore, there are actually several results that show Grover's algorithm seems to be particularly sensitive to noise. So as a result, this speedup doesn't seem to be implementable in the next few years. And furthermore, you can show that this general purpose algorithm only has a polynomial speedup. It will never achieve an exponential speedup for the general case. And this is due to a result of Bennett, Broussard, Bernstein, and Vazirani from 1994, in which they showed that Grover's algorithm essentially is optimal, these two papers combined. And actually, a very interesting bit of complexity theory history is that they actually knew the lower bound for this problem before they knew the algorithm. So sometimes the complexity theorists can beat the algorithmists in coming up with some of these ideas. But what this means in general is that this Grover speedup is not something we'll be able to do in the next few years. Now, fortunately for quantum optimization, this is not the end of the story. And why is that? Well, that's because in practice, when one faces optimization problems, oftentimes people use various sorts of heuristics that don't provably work in general, but they often can work in practice, and many times much better than a mathematical theorist, such as myself, would have predicted. And why is it possible for this to occur? Well, the main reason is that all of our theories of computational hardness, like this theory of NP hardness I've been alluding to, is about something that's called worst-case problems or worst-case instances. That is, they're trying to prove lower bounds on algorithms that are guaranteed to work, on any routing network you gave it, or any, portfolio optimization problem you gave it. And sometimes the hardness that's found in these computational problems is actually relegated to only some small subset of instances, some small corner. Maybe it only applies to routing graphs that look something like this, which is kind of some artificial, nice mathematical construction that's hard. But in the real world, you usually don't care about theoretical hardness results. You usually care about something called average case hardness, which is you don't care about how hard the problem is in the general case. You only care about how hard it is for the instances of the problem that you see in practice. For instance, the routing networks of real cities rather than kind of imaginary ones that a theorist dreamed up to embed some hard problem in it. And this gap between worst and average case hardness is what opens up the possibility of heuristics for certain problems in NP. Not for all problems in NP, I should mention. So many cryptographic problems do have what's called average case hardness. We think all the instances there are really hard. But for some optimization problems, there exist families of much easier instances. So this space for improvement has given rise to a number of near-term implementable quantum algorithms, which are various forms of quantum heuristics, which are trying to compete in this space of algorithms for average case problems instead of for worst case problems. So two prominent examples of this are the quantum approximate optimization algorithm of Farhi, Goldstone, and Gutman, and the quantum annealing algorithm, which is inspired by the adiabatic algorithm by the same authors in Sipser. And both of these algorithms are designed so that they'll be near-term feasible, but we don't yet have a good handle on how much speed up they'll have. And the reason is that because these algorithms are competing against these kind of classical heuristics, in which people make many different clever tricks for their particular instances, if you want to evaluate their performance, you're going to have to compare it to the performance of these classical heuristics that practitioners have developed over the last 20 or 30 years for these problems. So there's kind of an interesting interplay here between studying the quantum performance on near-term hardware and studying classical heuristics as they evolve and how well they can solve the same problems. In fact, Eddie Farhi will be giving some talk about some results in this area on day 3. So if you're interested in optimization, I would suggest you attend this session to learn more about this area. All right, so in short, if we want to plot where quantum optimization lies in this quantum algorithms landscape, Grover's algorithms and its generalizations fall in this box. So they provide a small speed up, which could be important or not, depending on how big of a bottleneck it is for you. But they'll provide these speed ups further in the future once we have error-corrected quantum computers. On the other hand, these kind of noisy, adiabatic, annealing algorithms and QAOA fall in this box as they have unknown speed ups, but they're something that we'll be able to implement and test out in the near future. All right, so this concludes the section on optimization. Are there any questions about optimization before I move on to the next topic? Okay, well, I can take some further questions on this at the end of the talk if people are interested. All right, so I'll now move on to the next application, which is quantum machine learning, which I'm sure many of you have just been waiting for me to get to. So, machine learning is in the news these days. It's kind of hard to ignore this if you live in the Bay Area. And why is this? Well, the short answer is that classical machine learning has found a ton of applications and revolutionized many industries. Everything from image processing, like how to search for images of cute cats on the internet, to things like language processing and translation, to self-driving cars. It seems like the wonders of machine learning never cease to amaze people. And since quantum computers, we believe, have some advantages over classical computation, it's a natural question to ask if they might be able to perform machine learning better than classical computers can. So this has led to a lot of press hype about quantum machine learning. Some of the press articles being very measured, such as this MIT Technology Review article, Machine Learning Meet Quantum Computing. Others of them slightly less measured. For instance, this article had the title, "If you think AI is terrifying, wait until it has a quantum computer brain." So this is why Jordanis Karanidis has called this the most overhyped and underestimated application of quantum computers. In fact, he'll be talking about this on day 3. Hopefully he'll illuminate, shed some more insight onto the hype and promise of this area soon. So given all this hype, will quantum computers be useful for machine learning? The short answer is that we actually don't know yet. And what's the difficulty here? Well, the difficulty for computational complexity theorists who try to study the power of algorithms is that classical machine learning is really an empirical science rather than a theoretical science. Namely, if you show the machine learning algorithms that people are using in practice these days, like deep neural nets, to a diehard computer science theorist, they will recoil in horror with the terrible shortcuts and hacks that they're using. These things are not provably guaranteed to work at all, but yet they work somehow. There's a lot of work in the theory of machine learning trying to understand why these work, despite the fact that they're tackling difficult problems. But the fact that this is empirical means that the algorithms are very difficult to analyze for theorists. And somewhat analogously with many of the quantum machine learning algorithms, we often can't mathematically prove that they'll do better than classical machine learning algorithms at their corresponding tasks. So what this means is that we'll basically just have to test them and see how they work. Ideally, it would have been nice if the theorists could have done some math and gazed into the future to see what will happen with their mathematical tools, but it's just very difficult for us to do this. So some examples of some quantum machine learning algorithms that fall into this category of heuristics for which we don't yet have strong evidence for hardness are quantum neural networks, which are some form of generalization of deep neural nets, which have been very useful in, say, image processing and many other areas, and quantum tensor networks, which is kind of a generalization of quantum neural nets. And I think the question as to whether these quantum machine learning algorithms are useful in practice will boil down to the following kind of philosophical question. Namely, if you have quantum patterns in your data, in some sense, then you would expect that a quantum device might be able to recognize them or exploit them more efficiently than a quantum computer, than a classical computer. So I think some of the question as to whether these heuristics are useful might boil down to whether these some sort of quantum patterns or non-local patterns in classical data are actually useful for classification and learning problems. And this is something that we'll just have to empirically resolve once we have near-term devices. Now, despite the fact that many of these algorithms don't have provable guarantees, there have been many works towards provable quantum machine learning algorithms. And most of these have used a paradigm called the HHL algorithm of Harrow, Hasidim, and Lloyd, which is an algorithm for solving linear systems of equations. So what do I mean by this? Unfortunately here I'm going to have to resort to an equation. So if you have a matrix A and a vector B, a fundamental problem in linear algebra is to find an x such that AX equals B. This is the matrix inversion problem. It's one of the most fundamental problems in linear algebra. And quantum computers are kind of natively linear algebra machines that do linear algebra on very high-dimensional vectors. And using this intuition, Harrow, Hasidim, and Lloyd were able to show that one can find the solution x extremely efficiently to these linear system solvers, namely in time which is only polylogarithmic in the dimension of the vectors. And this, in some sense, represents an exponential speedup over classical computing, Because in classical computing, you would have to say, read the entire input vector, which would take time linear into dimension, and do some matrix operations in order to solve the problem. But here, actually, one can do it polylogarithmically. So this is extremely fast. And because linear algebra is just so ubiquitous in all of theoretical computer science and machine learning, this has found many applications to many areas, such as recommendation systems, a paper of Karanias and Prakash, solving least squares optimization, ordinary differential equations, quantum finance, solving semi-definite programs. There have been tons of applications of this algorithm. But I should say, before you get too excited about this algorithm, that it comes with some caveats. The main caveat is that it's not near-term implementable. The main reason is that actually the HHL algorithm uses as a subroutine Hamiltonian simulation. So for the same reason that quantum chemistry applications seem to be more of a long-term application of quantum, similarly, the HHL algorithm is something that will only be applicable at intermediate to large-scale quantum devices. Furthermore, they require that the input to the problem be given in a special form. Namely, they assume that the input is stored in something called quantum random access memory, or QRAM. It's kind of a quantum generalization of the RAM model. It's not quite clear if that QRAM will be experimentally feasible. Another caveat is that it gives you limited access to the solution. So when I say that you found the vector x such that ax equals b, you don't actually learn all the entries of x, but rather you learn some quantum state that shares many of the properties with x. And so if you're willing to just extract a small amount of information from that vector, if that's good enough for your application, then this can give you an exponential speedup. But if not, then there's no free lunch. This won't necessarily help you. And the final caveat is that there is recent work this year, you might have heard on the blogosphere, by Ewan Tang and others, showing that certain variants of the HHL speedup can be reproduced classically. So this caused maybe a wave of fear amongst some quantum algorithms practitioners that Ewan Tang was going to single-handedly dismantle quantum computing by giving classical variants of all of our favorite algorithms. I can assure you this is not the case. That's because he only was able to dequantize some special cases of the HHL algorithm. And we know that the general HHL algorithm actually will still have exponential speedups because it's something called BQP complete as well. So as a result, there are a lot of caveats with applying HHL algorithm, which I hope Jordanis will talk about more in his talk on in the next day. And if you want to read more about these caveats, Scott Aaronson wrote a nice article entitled Quantum Machine Learning, Read the Fine Print, which kind of gives you a bit more of the subtleties and caveats that come when you're trying to apply these speedups. The speedups are there, but you just have to be very careful when you determine whether or not your particular problem is amenable to them. So in short, if we were to plot where these various quantum machine learning algorithms fall on the landscape, this HHL-based machine learning, at least the BQP complete versions that we don't believe will be dequantized, kind of sit up here. At least if QRAM is experimentally feasible, then they'll provide very large speedups, but these will be further in the future. On the other hand, these quantum machine learning heuristics like neural nets and tensor networks, some of them might be more near-term implementable, like some of the neural nets ideas, but we don't know yet how big of a speedup they'll have. This will end up being a matter of empirical implementation once we have access to larger hardware platforms. All right, great. So are there any questions about the machine learning applications before I move on? Okay, yes, great. Can you wait for the microphone? It'll be there a second. Thanks.
Would you mind saying just a little bit more about what you mean by quantum patterns in the data?
Sure. So one thing that we know about quantum systems, this goes back to Bell inequalities and kind of foundations of quantum mechanics, is that quantum mechanical systems can produce certain correlations between very distant variables, which are provably impossible to reproduce classically. So this is, this goes back to there's this famous Bell inequality violation that disproved hidden variable theories for quantum mechanics, which was experimentally demonstrated in many forms. And these sorts of non-local correlations are things that we know cannot necessarily arise in classical data. So I think this is maybe some sort of high-level idea for what some sorts of correlations might be there that we might have quantum access to. Maybe a second way to answer your problem would be that, in some sense, all of our quantum algorithms that exhibit exponential speedups, they all do so by taking advantage of certain forms of quantum correlations and interference in order to provide these exponential speedups over classical computing. And if these kind of interference patterns are present in the data, then this would be one reason to believe in a quantum speedup in the machine learning sphere. But whether or not cat images have those sorts of patterns, I have no idea. So, great. Okay, great. So I'm going to take more questions about this at the end of the talk. So let me move on to the next application, which is to cryptography. So there's also a lot of media hype about quantum computing and cryptography these days. Many articles saying that quantum computers are going to destroy the blockchain and all of cryptography as we know it. And as Vim mentioned in his talk, the reason for this hype goes back to the early days of quantum computing when Peter Shor showed that quantum computers can efficiently factor integers. And this is exponentially faster than the best known classical algorithm. And as Vim mentioned, this would allow quantum computers to break most crypto systems in use today, such as the RSA crypto system, Diffie-Hellman crypto system, essentially all of the crypto systems that underlie modern e-commerce, banking, etc. Now, do you need to panic? Do you need to go withdraw all of your money and put it under your mattress because people are going to crack internet security tomorrow? Fortunately, the answer is not yet at least. So as Vim mentioned, Shor's algorithm will require many qubits with error correction to implement. So it's not readily implementable on near-term machines. In fact, the largest integer that's been factored to date with Shor's algorithm is the number 21. Which is a number that's quite easy to factor, as we all learned in elementary school. So we have yet to see any implementation of Shor algorithms that seriously threatens, 2048-bit key RSA, say. But as Vim mentioned, this is a concern for long-term data security. And as a result, NIST, the National Institute of Standards Technology, is currently having a call for forms of post-quantum cryptography in order to establish a post-quantum public key cryptography standard that will eventually replace RSA as the backbone of public key cryptography on the internet. And the way that they're achieving this is through something called lattice-based cryptography. This is a form of public key cryptography which we so far believe is immune to quantum attack, and it's possible to make public key crypto systems based on this difficult problem. So in short, if you're worried about long-term data security, you might need to start worrying about implementing a post-quantum secure public key crypto system. But if you're just concerned about near-term security, then Shor's algorithm is not something one really needs to worry about. Now, I should also mention that quantum computers also bring some benefits to cryptography. In addition to destroying RSA in the long term, they also enable new forms of cryptography which are actually provably impossible with classical computers. So one example of this is something called quantum key distribution. And this is a form of cryptography which is secure only assuming that the laws of quantum mechanics are correct. So most cryptography is based on a difficult computational problem like factoring or lattice-based problems. This is a form of cryptography where you're basing its hardness or its unbreakability on physics. And in this model, there are two parties, Alice and Bob, who are trying to establish some secret key that they're trying to use to encrypt the communications between them. And if they were trying to communicate over a clear channel to establish this key, classically they would not be able to do so. And that's because if an eavesdropper were to listen into their conversation, it would be able to learn the secret key. But if the two parties share quantum entanglement, there's a property called the monogamy of entanglement, which says that it's not possible for a third party to learn their secret key in a way which Alice and Bob would not be able to detect. So this kind of eliminates the possibility of kind of eavesdroppers on the line between Alice and Bob. So this has gained a lot of industry interest as well as government interest. And this quantum key distribution protocol has been implemented, for example, over hundreds of kilometers over fiber optic networks, and also famously within the last year on a Chinese satellite which implemented quantum key distribution. So in short, this quantum key distribution kind of shows us that quantum computers are a double-edged sword when it comes to cryptography. They both destroy some old forms of crypto, but they also create new forms of cryptography, which maybe we couldn't have even imagined before. All right, so if we were to summarize these applications of crypto, breaking crypto systems is a long-term application that will have a very large speedup, but we have ideas for how to get around it by implementing lattice-based cryptography. And quantum key distribution is something that appears to be more near-term feasible and could be important if you're a person who has, if you're a player that has very high data security concerns, and you really want these sorts of guarantees. All right. So due to lack of time, I'm going to defer questions to the end and just move on to the final application of quantum, and this is quantum supremacy. All right, so quantum supremacy is also something which you hear a lot of news articles about these days. Some of them, again, more measured than others. And what's behind the supremacy hype? Well, the goal in quantum supremacy is to perform a practical demonstration of a quantum computation that's prohibitively hard for classical computers. And what's the basic idea here is the goal is to find some computational task which is near-term feasible and which has an exponential speed up over classical. So it has to be in the upper left-hand corner of that diagram. But in order to get there, we're going to relax something, and namely, we're going to relax the requirement that the algorithm is useful for anything. And there have been many candidates proposed for this quantum supremacy experiment. Some prominent examples are called boson sampling, IQP, random circuit sampling. There's been a rich theoretical literature on this topic. And as I mentioned before, unfortunately, these proposals don't seem to be useful on the surface. Why is that? Well, these proposals, instead of solving some optimization problem or breaking some cryptographic scheme, instead of doing something like that, rather what they do is they produce kind of random-looking output which contains some form of quantum correlation, some sort of non-local correlations, which we believe are very difficult to reproduce classically. And their main purpose is not really to do anything useful, but it's rather just to convince us that some near-term speedups, exponential speedups, actually exist. And kind of once we've proved to ourselves that near-term speedups actually exist in the upper left-hand corner, that will give us the confidence that we need, theoretically, to move in and try to find more practical speedups for problems that are more of interest. Now, even though these supremacy results seem useless, there's actually been some very interesting recent work by Scott Aaronson this year, which showed that these quantum supremacy experiments might be useful for producing something called certifiably random numbers. So these are random numbers which you can prove to someone were truly random. In other words, you could prove that you didn't secretly rig them to be non-random to have some subtle correlations that in them. And if you're just running a normal algorithm, you need some random numbers to run it. It might not matter if your numbers are certifiably random or not. But if you're in a very sensitive application like cryptography, then you might care very much if someone has snuck some correlations into your random numbers that they could use to break your crypto system. So this certifiably random numbers paradigm could have some applications of cryptography. And actually, Scott Aaronson will be giving a talk on these on day 3, which I would highly recommend you attend. So in short, these quantum algorithms for supremacy are things that we've engineered to be in this upper left-hand corner. The quantum supremacy tests are not necessarily useful. Rather, they're trying to convince us that something exists in this upper left-hand corner. This is like the holy grail of quantum algorithms research. And now the goal is to find some applications that exist in this upper left-hand corner. And certifiable randomness is one candidate for something that could be helpful there. And it would be really nice to have an optimization or another sort of algorithm that falls into that category. All right, so to summarize, what have we seen? So we've seen many different quantum algorithms that have many different domains of applications, like cryptography, simulating quantum systems, optimization, machine learning, supremacy, random number generation. I should mention that this isn't an exhaustive list. Many people work on topics like quantum sensing and quantum internet, quantum networks, which I haven't even had time to touch on today. But one thing that we've seen is that the algorithms that provably work often aren't feasible on near-term devices. So this gives rise to kind of the major challenge of the field, which is to try to develop useful algorithms for near-term devices which have provable speedups. In other words, what we want to do is to move from this areas of the algorithm landscape to the upper left-hand corner. That is to find miscue speedups which are exponential in size. I think this is the major problem that we face as a community, and something that I think there'll be a lot of work on in the near term as we have more access to large-scale quantum machines. All right, and with that, I'll conclude my talk. Thank you very much. I'll take questions. Yes, I see one up here. Yeah.
So Adam, that was a beautifully structured talk.
Thanks.
But it raised some questions for those of us who might have a classical computing training background.
Sure.
And one of those questions is, we often learn in classical computing about memory trade-offs, power trade-offs.
Mm-hmm.
You've emphasized speed up throughout.
Yes.
If you behave like an oracle sitting in front of us and try to predict the future, do you expect that there could be benefits beyond speed up? I think Wim made allusions to compression in ML kinds of applications.
Mm-hmm.
Do you want to make any predictions about other ways that there could be benefits?
Sure, yeah. So there certainly can be time-space trade-offs in computational problems. I guess the reason that people haven't been focusing on them as much recently is that we haven't had that many qubits to work with. So the concept of having a quantum algorithm where we have a whole lot of space to work with just isn't something we've been presented with yet, if that makes any sense. But yeah, I certainly agree that there might be some possible work in the future on trying to take quantum algorithms and say parallelize them better, or maybe there might be quantum algorithms that are more easily parallelizable than classical algorithms, such as studying quantum NC1 versus classical NC1 for the experts in the audience. Yeah, so I agree this could be a direction of future work. Yeah, thanks for a question.
Hi. So it might be just semantics, but I was wondering why you separated finding physical systems ground state from an optimization problem.
Yes, that's a great question. So yes, so actually finding the ground state of a quantum system is itself an optimization problem, as you pointed out. In fact, it's an optimization problem which is, in general, even harder than an NP-hard problem. It's something called a QMA-hard problem, which is a quantum generalization of NP. So there actually is an even bigger complexity theoretic barrier there to finding algorithms for these problems. But the reason that I put this more in the quantum chemistry side is just that's one of the places people are most excited about using this optimization algorithm. But yes, in general, one might be able to use these kind of hybrid quantum classical optimization algorithms for classical optimization problems as well. Yeah, that's a great point. Thanks.
Again, in the optimization section, you said that Grover's algorithm is inherently deep, and that's one of the drawbacks. Is that because the eval function has to be inside the quantum circuit, or is that endemic to the
Yeah, so
problem
this
itself?
is actually in, yes, so there's one problem is that the eval function of your database query has to be done in superposition, but it's actually, the problem is a bit worse than that. You actually have to be able to do many of these eval function evaluations. You have to be able to perform it with a substantial depth in order to see the speed up. So not just to do it once, but you have to do it many times. So if you do it depth d times, then you can get a d-fold speed up over classical. And if your quantum clock rate is a lot slower than your classical clock rate, that means it might take you a big depth in order to start seeing a performance improvement there.
All right, that brings me just to the quick second part
Sure,
then.
sure.
If that's the case, these long duration coherent circuits like the Mariana fermion and that kind of stuff, will that make this a lot more amenable?
Yeah, so if we see large-scale Majorana fermions, et cetera, then if these things are more robust to errors, then yes, it could be more helpful for Grover's algorithm or any of the algorithms I put on the right-hand side that will require more error correction. Yeah, the intuition there is that those physical systems just might be more intrinsically robust to noise. Yeah, we'll have to see how the hardware progresses in terms of whether we see these systems in the near term.
Just one more quick. So if you can have that, can you do a hybrid thing where the evaluation function is outside, or is that just absolutely impossible because the outside system can't be inside the superposition? Or
Yeah, sure. Yeah, I think you actually need the function evaluation to be done in superposition. If you do it on a classical computer on the side, it will kill the quantum speed up. Yeah, that's a great question, though. Yeah. Very good. Yes.
Hey, way to get back over here. Yeah.
Okay.
Is there a reason you separated quantum neural networks from quantum tensor networks as near term versus long term? Because we know that quantum tensor networks have these NISQ algorithms being developed, like for DMERA, and MPS that have, a polynomial speed up relative to contracting tensors on a classical computer, and we think this could be useful for, condensed matter physics and so on.
Great. So that's a great question. Yes. So there have been many proposed quantum algorithms which use tensor network ideas that are more near-term feasible. Like, as you said, these ADS mirror correspondence algorithms and stuff like this. But these algorithms all have the property that it's relatively easy to prepare the state that the mirror represents on a near-term device. Whereas actually for general tensor networks, more general tensor network paradigms, sometimes it's actually very difficult to prepare the quantum state that corresponds to the tensor network. So there are polynomial time algorithms there, but just they're somewhat slow. So so I agree. There are some tensor network things that will be in the miscue era, but the more general ones actually seem to be a bit harder. Yeah, that's a great question. Yeah.
So when we consider the quantum applications, I think we will not really put the classical algorithms in the completely opposite side. So what would you expect the classical algorithm will be used or be helpful in developing the quantum algorithms?
Oh, so do you mean the classical evidence with say, optimization problems like
yeah, so for example,
heuristics.
I know that in the quantum chemistry field that we use hybrid algorithms
Yeah,
to
of course.
overcome the error problems. So what about the other applications you listed in the talk? Thanks.
Yeah, sure. So in general, yes, whenever we're trying to compare quantum algorithms to how well they perform in practice, you always need to compare against the state of the art on the classical side. And I agree that in quantum chemistry, that might be, for instance, some various DMRG or density functional theory sort of methods that people are using to handle these for now. So I think that actually probably what we'll see is a kind of a rich interplay between quantum algorithms and the classical heuristics that are used. As they might end up kind of leapfrogging one another for a period of time on the heuristic side. For the quantum algorithms with provable guarantees, this might be a more lopsided race between the two sides, because there you might expect the quantum algorithm might have a more intrinsic advantage. But we've already seen this, for example, I'm sure Eddie will talk about this on day 3, but there's a brief period of time where the QAOA outperformed the best classical algorithm for some version of maxcut. And then, as Eddie put it, a whole bunch of classical theorists ganged up on him to make a better classical algorithm that then beat the quantum one. So yeah, so it could be that actually some of these quantum algorithms stimulate new ideas in classical optimization that improve classical optimizers as well. This is similar to Ewan Tang's work as well, and many others who've worked on that. Yeah. Good. All right, I see one back there.
Isn't the linear algebra solutions on quantum computer limited to a certain class of matrices with the sparsity and unitarity property?
Yes, that's exactly correct. Thanks for bringing that up. So I listed a lot of caveats to the HHL algorithm. That wasn't even a complete list. The thing is that the HHL algorithm requires some additional conditions on the matrix. The most problem is that it requires the matrix A to have a low condition number, which is a low ratio of its minimum to maximum singular values. And this may or may not be a reasonable assumption to make depending on your problem of interest. And many of the special variants of HHL algorithm make even further assumptions beyond that, like sparsity or low rank. So yeah, so thanks for pointing that out. There are even more caveats there. Yeah, great. All right, great. And with that, I'll conclude. Thank you very much for your attention.